This is lesson number 2 inside of the first part of Unit 5 for college algebra. In this video we are going to focus on what we call the rational roots theorem, or sometimes called the rational zeros theorem. This theorem, along with some other algebraic processes, will allow us to find every rational zero or every rational root of some polynomial p. And one thing that I want to point out is that zeros and roots directly lead us to factors. And so in the last video we were talking about this process a little bit, how these factored results, these factored polynomials were pretty nice for us because they gave us a pretty good understanding of the behavior of a function. When we knew where the factors existed, such as all of these examples here, we were able to predict and determine how the function itself would behave. So by the end of the video, we were faced with this question, and I told you to skip it for now and maybe research it on your own, but essentially we were reminded that zeros of polynomials also indicate factors of polynomials, and I wanted to see if you were able to factor this, especially if we know where at least 2 of the zeros exist. Now, if you were on your toes, you would have realized that this function, 3x cubed minus 3x squared minus 99x minus 189, is awfully familiar. It is precisely the function that we were dealing with in this example just a few moments ago. So how is it that we take the original polynomial form of the equation and factor it into this factored form? Well, the technique that we need is called polynomial long division. Polynomial long division. And sometimes we can get away with what we call synthetic division. Synthetic division gives us a quicker way to complete polynomial long division, but it doesn't work in all cases. It only works in specific formats. So in the remaining moments of this video, I'm going to chat a little bit about these division techniques. I'm probably going to focus more on synthetic division, but I would highly recommend watching some videos on these two techniques. Go out and search YouTube for these phrases, or search the internet for other websites that talk about these techniques. It would be very, very beneficial for you to become a little bit more comfortable with these processes. Perhaps you've seen them in the past, or maybe you've never seen them at all, but it is definitely worthwhile to take some time to practice. So back to the rational roots theorem and why this is so beneficial to us. Remember, our goal with a lot of these functions is to interpret their behavior without relying on the graph. Now, in these conversations, in these notes, and in these initial stages of this work, we end up recreating the graph, but that's my way of just verifying your understanding, or indicating how our interpretation can be visualized. But again, by understanding important components of this equation without relying on a graph or other analysis might allow us to interpret the behavior of the function in a real-world context just a little bit better. So in this particular case, we're being asked to list the potential rational zeros of this function. Now, based on what you know from Algebra 2 and the reminder that I provided in the last video, we have a positive leading coefficient with an odd degree. So I know that the right tail of this polynomial is pointing up and the left tail is pointing down. I also know that this graph will cross the x-axis at -6. We also know that the behavior of this function would imply that there are at most 2 turns. Now, where those turns occur and other important components of this graph are unknown at this point. This graph could have 2 big turns like this. They could be relatively shallow like this. We just don't know. And if we knew the zeros where the graph touches or crosses the x-axis, if it happens 1, 2, or 3 times, well, that additional information will provide us some clarity on the shape and behavior of this function. So identifying these zeros are important. Now, where are the zeros? Where can we find them in this function? Well, remember that a zero occurs whenever I substitute a number in place of x. Let's just make a guess, 3. I don't know if this is true or not, but if I were to substitute the number 3 into this expression, then the result of this calculation should end up equaling 0. So again, when I substitute the number 3 into this expression on the right-hand side, in order for 3 to be considered a 0, and in order for this x-intercept to be located at an x value of 3, then the entire equation has to equal 0. And to be perfectly honest, there's an infinite number of x values in which this can occur, because there are an infinite number of rational numbers, or numbers in general, along this x-axis. So how on earth are we going to find the x values that make this equation equal to 0? It'll be virtually impossible to guess and check to find those solutions. So this rational roots theorem, what it does is it gives us a list of numbers to test. Because again, every rational zero, now it's not every zero of the polynomial, it doesn't have to be every zero of the polynomial, but every rational number 0 will be in this particular form. And if we create a list of numbers that meet this criteria, then we can start off by testing those numbers in that list. And if we find all of the zeros, great. Even if we don't find all of the zeros, we can use them to factor and reduce the size of the remaining polynomial. So let me just kind of remind you and point out some things from this rule before we use it. The polynomial, we'll often use p of x instead of f of x for a polynomial, is in this particular form. And what we're saying here is that we have, because we're running out of letters in the alphabet, a times x to the nth power plus b times x to the n minus 1 power plus c times x to the n minus 2 power, and so on, all the way until we get down to the last component, z times x to the 0th power. Since the alphabet only contains 26 letters, we don't use individual letters for the coefficients in this list. Instead, we use the letter n with subscripts, and these are our way of showing essentially an infinite number of coefficients that are possible in an infinitely large polynomial. And again, these coefficients must be real numbers. They can be decimals, they can be non-repeating values, they just have to be real numbers, but our exponents themselves have to be positive, or I should say non-negative integers. So in each case we have a non-negative integer exponent. Now, in order to create a list of potential factors, we're going to take the factors of the coefficient, the value at the very end of the polynomial, and the factors of the leading coefficient. Sometimes we call this one, by the way, the trailing coefficient. So it's the coefficient at the very end of the polynomial. And we take those factors and divide them by the factors of the leading coefficient. And that's going to produce a list of potential rational zeros. So here we go. The trailing constant in this case is -6. So I'm going to list this as p. And our leading coefficient is 2. So I'm going to list that as q. Now technically p is not equal to 6 and q is not equal to 2, but we're going to use 6 and 2 to produce a list of factors. These factors are the p values and q values that we're after. So with number 6, I know that the factors, or the numbers that divide 6 evenly, have to be somewhere between 1 and 6. 1 times 6 equals 6. So if I'm creating a list of factors, the smallest factor is 1 and the largest factor is 6. Any other factors of this number have to exist in between. And so I'm just going to step up one number from 1 and investigate the number 2. Does 2 go into 6? Well, certainly it does. And 2 times 3 equals 6. So now I have a list of numbers. If there were any additional factors to the number 6, they would have to exist between 2 and 3. But since there are no other whole numbers between 2 and 3, then I know I now have a complete list. And I may even clean up the format just a little bit. Same thing is done with the factors for Q. Well, the smallest factor is 1 and the largest factor is 2. Are there any numbers in between 1 and 2, any whole numbers I should say, that evenly divide the number 2? Well, that answer is no. So our entire list of factors for Q are simply 1 and 2. Now, I did ignore the negative symbol here, and we could have included it, but traditionally we don't. And the reason for that is, whether there's a negative number here or not, when we're listing the potential, and I've been saying whole numbers, I should be saying integer factors of 6, we should recognize that both positive and negative forms of each of these numbers can evenly divide this original value. Again, whether it's positive or negative, these integers, either positive or negative, can still divide it. 6 can be divided by 1, 6 can be divided by negative 1, and produce an integer result. So when we produce our list, before we're done, we should at least recognize that 1, 2, 3, and 6 are not just the only factors of the number 6, but so are negative 1, negative 2, negative 3, and negative 6. So these are the factors of P, and these are the factors of Q. If I'm going to create a list of potential rational zeros, then I need to take every entry in the list of P and divide it by every entry in the list of Q. Now this could get time consuming, especially if there are many, many factors for P and Q. So developing some sort of pattern here when creating this list is going to be important. Here's how I usually do that. I'll start with every element of P, 1, 2, 3, and 6, both positive and negative, and divide it by the first element inside the list of Q. So I'm thinking to myself, well, what would happen if I took a positive 1 and divided by a positive 1? Well, that leaves me with 1. What if I took a negative 1 and divided by positive 1? Well, that gives me a negative 1. Now, if I took a positive 1 and divided by negative 1, well, I get negative 1 again, and I don't need to list that a second time. And if I took a negative 1 and divided by a positive 1, well, I get a negative 1, and I don't need to list that again. And I may have misspoke, but I think you're getting the idea. Hopefully you're getting the idea. Whether these coefficients are positive or negative, when the number 1 divides by 1, we will end with the result 1, both positive and negative. Similarly, if I take the number 2 and divide it by 1, positive 2 divided by positive 1, negative 2 divided by positive 1, positive 2 divided by negative 1, and negative 2 divided by negative 1. In all of those divisions, we are going to end up with 2, either positive or negative. Moving on to 3, if that's divided by 1, we end up with a positive or negative 3. And then finally, positive or negative 6. Now that only takes care of half of our potential rational zeros. That's all of our P values divided by the first Q value. Well, what's going to happen if I divide my P values by the second Q value? This time, 1 divided by 2 in both positive and negative forms. Well, that produces the number 1/2. 2 divided by 2, well, that's okay. That equals 1, positive and negative, and we've already got that in the list. Now 3 divided by 2, well, that's 3/2. That's not in the list yet. Positive and negative 3/2. And then finally 6 divided by 2, well, that's 3, and that's already in the list. So as you can see with the pattern, essentially the list of p-values get repeated first. We list those again because all of these p-values divided by 1 just recreate the same p-values. Then when we take the p-values and divide by the next q value, we added a couple fractions as a result, which are rational numbers, but there weren't too many to be added, and we would just continue that process all along. So what we've done at this point is we've created a list of all potential rational zeros. Of the infinite number of zeros that could exist, if there are going to be any rational number zeros, they will be found in this list. There will be no other rational zeros outside of this list. And so that's pretty nice for us because, again, with an infinite number of possibilities out there, an infinite number of rational numbers that exist in the real number system, the only rational numbers that might produce a zero will land here. So if we take this understanding now and the conversation from before, if we're looking for zeros or values where the equation will equal 0 when evaluated at these numbers, then what I should do probably is reach for a calculator to make this go faster, but we should evaluate the function, sorry, this is p of x, the function was a polynomial, and evaluate this polynomial at all of these potential zeros. So I'm just going to make a list here, and then I'm going to start up the calculator. But we have 1, 2, 3, 4, 5, 6 numbers, both positive and negative. So there are basically 12 values that we should be investigating. So I'm going to take a moment to create this list, and then we'll reach for the calculator and start testing these numbers. So again, there are 12 values that I'm going to investigate inside of the polynomial. And we need to keep in mind that this polynomial, oh, it was named f of x, my mistake. But that's okay. We'll call it p of x from here on out. This polynomial can have at most 3 zeros. It can turn 2 times, but there will be at most 3 zeros. The graph will touch or cross the x-axis at most 3 times. So even though there are a list of 12 numbers here, it's possible that 1, 2, or 3 of them will equal 0. So let's see if we can find them. So I'm going to turn on the calculator and open up a calculator page. And I'm going to rewrite this function, not with the letter x, because the letter x, y, and z, those variables are often stored in the calculator elsewhere for specific use. I'm just going to use the letter a right now. 2a to the 3rd power plus 11a squared minus 7a minus 6. And I'm going to press enter. This is going to store this function in the calculator, or at least enter it into its memory for just a moment. And then what I'm going to do is I'm going to run through all of these test points by storing the number 1 in place of the letter a, and then re-execute the expression. So if you recall, we can place the number 1 on the screen and press Control Variable. This will allow us to store a number as a variable. I'm going to store the number 1 in place of a. Now, when I jump up here and press Enter to copy this expression down, the letter A is a bold letter now. That means it's got a numerical value associated with it. And when I tap Enter, the calculated result is equal to 1. So evidently, 2 times, is equal to 0. So evidently, 2 times 1 cubed plus 11 times 1 squared minus 7 times 1 minus 6 does equal 0. And that's pretty great, because we just found one of our zeros. Let's try that again with the number -1. So we'll take the number -1 and store it as a. This overwrites the previous value. Now when we execute this expression, we see a result. Now that one came out to be 10. That's not good for us because that is not a 0 of the polynomial. So let's test number 2. We'll store 2 in place of a, re-execute the expression, and that one comes out to be 40. And we're going to continue this process until we test all 12 potential zeros. Or, if you're keeping in mind that there can only be 3, or at most 3 zeros, it's entirely possible as well that we find 3 results before we get to the end, And if we do find 3 results before we get to the end, then we can stop, because again, there can be at most 3 zeros. So I'm going to pause the video now, and I would suggest that you do the same and try completing the rest of this list. How many of these other values do contain a 0? Resume playback in a moment to check your work. Well, as I was running through my examples here, I ended up finding a 0 at -6. So I tested 3, then -3, 6, then -6. I tested 1/2, and then -1/2. But at this point, I found my third 0. And again, there can be at most 3 because the exponent, the degree I should say, is 3. So there are no more than 3 zeros in this polynomial. So I didn't even bother testing 3/2 or -3/2. There's no need to do so. I know that those won't produce a 0. So this is pretty good for us. We had a list of potential rational zeros, and to be honest, if the question only included this, then we would stop with this list here. But the instructions did, and I forgot to point this out, said to also find the rational zeros and write the function in factored form. Well, fortunately for us, we found all of the zeros, so therefore we have all of the factors. Keep in mind that a 0 exists. I'm going to go back to this f of x notation because that is what was given to us originally. Keep in mind that every 0 directly relates to a factor. Now, the factor that utilizes 1 as a 0 is x minus 1, because 1 minus 1 equals 0. The factor that utilizes -6 or produces -6 as a 0 is plus 6, because -6 plus 6 equals 0. And then finally, the factor associated with the 0 of -1/2 is x plus 1/2. Now, this format will reproduce all 3 of these zeros. However, it will not reproduce the original function. In order to reproduce the original function, we generally eliminate factors in their fractional form. So certainly, when x plus 1/2 equals 0, x by itself is -1/2, and we have our 0 that we found in our list. So that's okay, but a better way to list these in factored form is like this. If we were to eliminate the fraction, in this case we eliminate the fraction by essentially multiplying by 2. Let's multiply both sides of this equation by, whoops, this was equal to 0. Let's multiply both sides of the equation by 2. We can do that because that preserves the balance of the equation, but it's going to change the look of this expression over here. Now, when distributed in, we're dealing with 2x plus 1 equals 0, and this is the factor that I'm going to use in place of this. And that's okay, again, because we established it using appropriate math skills, but also if we were to check this by subtracting 1 from both sides and then dividing by 2, we again have a solution, or a 0, that exists at -1/2. The exact same as what we saw a moment ago. By reporting our function this way, this x minus 1 and x plus 6 was fine, but now calling this last factor 2x plus 1, when we distribute these binomials or FOIL them back together, we will end up with the same 2x cubed plus 11x squared minus 7x minus 6 that we started with. An easy check for that is to look at your leading terms within each binomial. X times 2x does equal 2x cubed, and -1 times 6 times 1 does equal -6. So if you check those two, at least you'll have a pretty quick understanding if you're on the right track. You would have to continue to FOIL and distribute to find these middle two terms. But I got a little sidetracked there, and the point I wanted to make here was that we can recreate the graph of the original function by now recognizing where the zeros exist. And I did cheat a little bit, and I provided a screenshot from the calculator on your notes here. you'll notice that the zeros exist at -6 here, at -1/2 here, and then again at 1, which is right here. Even if we had started with our own xy axis and placed a point at -6, a point at -1/2, and a point at 1, we should be able to recognize the behavior of this graph. Again, the right side tail points up and the left side tail points down, and they emanate from these right and leftmost zeros. We see that here as well. Each of these zeros are linear in nature. There is no multiplicity associated with them. So at each zero, the graph sort of behaves like a linear function where it goes straight through that zero. And in order to maintain the smooth and continuous behavior of the graph itself, we have to have one turn here and one turn here. We have at most 2 turns because the power is 3, and at most 3 zeros because the power is 3. And this sketch, hopefully produced mentally or on a piece of paper, does indeed match the characteristics of the actual graph produced by a calculator. So let's try those techniques again in our next example. Find the real zeros. Now that phrase is a little bit different. Real number zeros of f of x, and write f in factored form. So it may be a little bit more difficult to find all real number zeros, but let's start with the rational zeros. We can use the rational roots theorem to find the rational zeros first. Once we have the rational zeros, then we'll see if we can use any other tricks to find the remaining zeros. So I'm going to start off by listing P and Q. P is the value at the end, our trailing constant, and Q is our leading coefficient. So we'll call that the number 1. Now this is nice because the factors of 1 are simply positive and -1. And the factors of 48, well, I'm going to use my list method here. We've got positive -1 and positive and -48. The next 2 factors that exist have to be somewhere between 1 and 48, so I'm going to guess 2. And I know that 2 goes into 48 24 times, so I'll list 24 next. Try to give myself some room here. Now the next 2 factors have to exist somewhere between 2 and 24. Well, that ends up being 3 and 16, and any additional factors exist between 3 and 16. That's going to be 4 and 12. I'm running out of room here. I didn't give myself enough space, but the last 2 are going to be 6 and 8. And if any additional factors exist, they would have to be between 6 and 8. The only number in between 6 and 8 is 7, so I know that 7 doesn't go into 48, so I know my list is complete. Now as far as P divided by Q goes, the actual list of potential zeros, we take every element from the list P and divide it by every element in the list Q. Well, that's not too bad because essentially all of these P values are only being divided by 1. So the potential zeros are the same list of factors of P. Now, I think we can get away with listing our values this way. I don't know if this is mathematically appropriate, but I think it'll convey the message, so I'm okay with it. I'm going to put my positive and negative sign in front of the list, and that way inside this list I'll only report the numbers themselves. This will be a good way to indicate that all the numbers in this list can either be positive or negative. Now here again we've got a fairly large list, and we should investigate the function results at each of these positions. So let's go ahead and set up a table and do that now. And here they are. Again, this is quite a large list, and it will be a bit time-consuming to test all of these numbers. But you know what? It's better than the alternative. It's better than investigating an infinite number of numbers, because now we only have 20 values to investigate. It could have been an infinite number of numbers, but this time we only get 20 of them. Now again, keep in mind that we're only interested in the results if they equal 0. If these don't equal 0, I don't care what number they are. I'm just going to make a note that they are or are not equal to 0. So I'm going to pause the video, and I'm going to expect that you do the same. So please try to find these zeros on your own as well. I thought I'd jump back in here and point out we're off to a good start. I tested 1, -1, 2, -2, 3, and -3. These first ones weren't 0. I don't even remember what the numbers were, but they weren't 0, so I'm going to cross them off. This one was not 0. This one was not 0 either. So I'm just indicating that the function at 1 is not 0. The function at 2 is 0, and I'm going to highlight them. Now, I may not have to go through this entire list because, again, there could be at most 5 zeros. I found 2 of them already. Let's see if we can find the other 3. If we find the other 3 before we reach the end, then there's no need to test the others. So I'm going to move on to the rest now. Well, I had to open my mouth, didn't I? Evidently, there are only 2 rational zeros in this entire list. There could be as many as 5 real number roots. So if we only found 2 zeros, and these are all of the rational number zeros, then that means that if there are 3 additional real number zeros, we're going to have to find them using some other technique. Or what might even be more tricky is that there could be multiplicity in this polynomial, and this 0 and this 0 might end up showing up more than once. So usually before I test for multiplicity, I'm going to run through synthetic division to factor. And after I'm done factoring, I'm going to take a look at the result that remains and then decide what to do from there, whether I use, say, a quadratic formula or some other technique to find the remaining zeros. Now again, synthetic division is a process that's generally covered in Algebra 2. If for some reason you didn't see it in your Algebra 2 class, or if you didn't see it in a pre-calculus class before you took college algebra, go out and spend some time revisiting this, or see me before school or after school for extra help to clarify this process. But with synthetic division, what I'm going to do is I'm going to create this L chart, and on the outside I'm going to indicate the 0 that I want to test first. I'm going to start with number 2. Now inside the L chart in the top row, I'm going to list all of the coefficients of the original polynomial. So I'm going to start with 1, -1, -4, 8, -32, and 48. And with the synthetic division process, this is just our way of abbreviating the long division form. This synthetic process only works if we have found at least one rational number 0. And since we did find a couple of those, then using the synthetic division process is just fine. Now to begin the process, the instructions remind us to drop this 1 down. This coefficient of 1 in our original polynomial will end up being the coefficient in the dividend, or the result of the division in the next polynomial. So that always comes straight down. Then the next process, or the next step in the process, requires us to take this outside value 2 and multiply by the 1 and report that result here. 2 times 1 is 2. Within this column, now that we have a stack of numbers, we're going to add these 2 together. -1 plus 2 is 1, and we're going to repeat the process again. This time the number 2 multiplies by this 1. We get 2 again. Since we have 2 numbers that are stacked, we're going to add those 2 values together. -4 and 2 is -2. We're going to continue that process all the way down the line. We knew that this value 2 was a 0 of the polynomial, and this 0 at the end just verifies that. So if you end up with something other than 0 at the end, then either A, you made a mistake with your math along the way, or B, this value wasn't really a 0 to begin with. Now, what I would like to point out is that this first step of synthetic division has simply given us the information to factor this polynomial. We know that the polynomial was equal to this 5th degree polynomial to begin with. But if I were to factor out the polynomial x minus 2, and we're using x minus 2 because that's the opposite of the 0, 2 minus 2 is what equaled 0, then the factor that remains after dividing by x minus 2 is the coefficients of this result from the synthetic division, starting with x to the 4th power, 1 degree less than what we began with. So we have x to the 4th plus x cubed minus 2x squared plus 4x minus 24. Now, if you have an idea of how to factor this, then I would suggest factoring on your own. But this is a 5-term polynomial, 4th degree. I'm not real familiar with how to factor that, so I'm going to continue the synthetic division process. The result from this step will now be synthetically divided by the number -3. And I'm using -3 because that was the other 0 that we found in our list. And so with the process again, I'm going to drop down this 1 immediately. That always happens. Regardless of the value here, we always bring that straight down. And then I'll continue to the process. I will multiply -3 by this 1, add these two together, and then continue. And this result gives us some further information. We had already factored out the term x minus 2 because of the first step in the synthetic division. We've now factored out x plus 3 because of the second term in the synthetic division. And each of these values represent the coefficients of another polynomial, this time starting with the exponent of 3, a degree of 3. So we have x cubed minus 2x squared plus 4x minus 8. Now we're down to a 4-term polynomial of a 3rd degree, and while I'm not real familiar or confident with factoring techniques here, there is one that might work, and that's factor by grouping. So I don't have any more numbers to check in my in my rational roots list. So I don't have any other numbers to check. If I did, I would probably continue synthetically dividing. But since I don't, I'm going to investigate my factoring techniques here. Now, when factor by grouping, these are untouched, so I'll copy them down. What we're looking for is a GCF in this first group, and what I notice here is that the value x squared is common to both terms, and that's, when factored out, is going to leave us with x minus 2. In this second group, I notice that the number 4 is common, so I'm going to factor out a 4. And what I'm left with here is, again, x minus 2. And that's a good sign for me because I see that these two factors are the same. And so that allows me to factor that group by grouping, or factor this polynomial by grouping, by indicating that the common factor here, x minus 2, ends up multiplying by the coefficients that remain, x squared plus 4. And as it turns out, this x minus 2, well, that is a duplicate of another factor from before, so it does indicate that we have multiplicity. We have x minus 2 squared times x plus 3 times x squared plus 4. I'm not going to bother factoring any further because I know that this cannot be factored. There are no two binomial groups that will multiply together to equal x squared plus 4 with real number components. If this had been x squared minus 4, that's a different story. That may be something you're familiar with, but x squared plus 4 cannot be factored. And as a side note, x squared plus 4 cannot equal 0 and produce a real number result either, because that would require the square root of -4. So with this factored form of the polynomial, I think we have enough information to sketch our graph. I'm going to start with an XY axis, and I'm going to cheat a little bit because I have this electronic ink available to me. I'm not too concerned about the scale at this point, but it's worth noting that the sketch should be realistic and reasonable. But this 0 here occurs at x equals 2. So I'm going to make a note of it. There's a 0 at x equals 2, and it's got a multiplicity of 2, so it's going to behave like a parabola. So it's going to bump into the graph and turn away, kind of like a parabola does. The 0 here, there's a 0 at x equals -3, but its multiplicity is 1, and we usually don't indicate that, but I'll make a note of it here. That means it's going to behave like a linear function. Now, because of this factor, there are no real number zeros, so we won't see those on the x-axis whatsoever. The only 2 points on the x-axis that this graph will touch is at -3, and I'm going to place that dot somewhere over here. I'll go ahead and put it on the grid line, that's okay. And then at +2, right there. Now, using some other analysis of this function, we do have a y-intercept at +48, so that's going to be somewhere way up here. Again, scaling's not provided, so I'm not going to be real critical. And because of the positive leading coefficient and the odd degree, I know that the right side tail of this graph is pointing up and the left side tail of this graph is pointing down. The graph will not touch or cross the x-axis anymore because we did not find any other zeros, but the remainder of this graph has to be smooth and continuous, and we have to strike these 3 points with a smooth and continuous line. Now, as far as a sketch goes, if we're predicting the behavior of the function, this would be a pretty good prediction because, again, the graph can have at most 4 turns because of the degree of 5. It could have at most 5 zeros, but we didn't find those 5 zeros, so it's unlikely that we'll find 4 turns in the graph. If I were sketching the behavior of this function, I think this would be a really good sketch. We could verify, of course, with the graphing utility, and that's what we see here. And the shape is generally the same. There are some discrepancies. Our prediction was that, or at least my prediction was that the graph would come through the y-intercept at a peak and then turn down and away. But this additional peak here would have required some additional analysis that we don't see right now. As far as I'm concerned, the sketch was pretty good, and when we compare that to the graph, I'm pretty satisfied with the result. Now, of course, if my sketch was backwards or if it had a couple extra turns to it with additional x-intercepts, that would have been wrong. That would have been no good. But most of the major characteristics have been accomplished with this sketch, so I'm happy with that. Now, I know that this video is running quite long. It's much longer than usual, but there was a lot to cover, and hopefully you've picked up some information about the process now. I would recommend that you go back to your notes from the last video, and if you didn't already do so, you can perform the same analysis here with this expression. We can look for rational zeros, although we were provided with 2 of them. We can use synthetic division to show the remaining factors after we're done dividing. And we too could produce a sketch of the graph and predict the behavior of that graph based on end behavior, zeros, and y-intercepts. And hopefully in the process of doing so, you would regenerate a graph that does look like our predicted solution from here. If you have further questions about the work that was completed today on the rational roots theorem, please reach out to me, do some research on your own, or talk to one another for help. Thanks for watching.